So let us then talk officially about buffers. We've been sort of alluding to buffers, and really a buffer solution is a really common ion situation that's occurring. And a buffer is really made up of really a combination of two things. You could either have as it says there, a weak acid and the salt of its conjugate base. The salt just means that it has like a spectator ion that's really not doing anything, like a sodium, a potassium, something like that, lithium. Or you can make a buffer out of a weak base and the salt of its conjugate acid. They both need to be in solution to begin with. And that is really why it has to be a weak acid and this conjugate base, or a weak base and its conjugate acid. You cannot have a buffer that is from, or made up of, I guess is a better way to say that, made up of a strong acid or a strong base. So you cannot have a buffer that's made up of a strong acid or a strong base. And it's really for this reason. As it says here, they both have to be present in the solution in order for a buffer to work correctly. So for example, if I took something like hydrofluoric acid, like we were just talking about there, and a solution that has sodium fluoride in it. This is a weak acid. And this is its conjugate base. This is really the salt of its conjugate base because frankly, there is a sodium there. The actual buffer part is not the sodium, it is actually the F- part. It is actually the buffer part of this. It's really the HF and the F-. The relationship between these two things is a difference of 1H+, like we talked about with Bronsted-Lowry acid-base conjugate base pairs. That's how you can know if these things can be a buffer, is they need to be related to each other by that kind of Bronsted-Lowry definition of just 1H+ difference between them, and they do need to be weak. So when we have something like HF and sodium fluoride as sort of our weak acid and salt of its conjugate base, what happens in solution is that hydrofluoric acid, as I drew on the last one there, will be able to set up an equilibrium where it will be able to keep in solution both parts of that buffer that's needed. It's basically the acid part and the base part of the buffer. And in this case, we're actually going to have a little bit more of that F- than we normally would, because we're going to add some sodium fluoride to it. So we got to kind of beef up the F- part of the buffer in there. But that allows both of those things to be in the solution to begin with, and that's really important for how a buffer is able to function. Why we can't do that with like a strong acid, for example, is when I put a strong acid, like say hydrochloric acid, and I want to make it a hydrochloric acid and sodium chloride. They are related to each other, right? We have HCl and Cl-. The difference is 1H+ between them. The problem, though, is hydrochloric acid is a strong acid, which means when it goes for a swim, it is going to 100% break apart into H+ and Cl-, right? You got H+ and Cl-. You have a little bit more Cl- from the sodium chloride. You have some sodium ions in there, which is not doing much. That's neutral, so it's not doing much. So really what you would have in this situation is, because that is a strong acid, it cannot set up the equilibrium. And really the only thing that you would have in that solution is kind of like the conjugate base. You would have none of the acid part still in the solution. And that is why a strong acid or strong base cannot be a buffer, because it's not able to keep both the acid part of the buffer in the solution and the base part in the buffer solution. You'll just have one or the other, and it will not be able to function correctly. Yep. Yeah, because HCl, if we look at like we wanted to make a buffer with HCl or sodium chloride together, right? Just like we dumped HF and sodium fluoride in there. If we dump both of those things in there, they're actually both strong electrolytes. The sodium chloride is a strong electrolyte, and so is hydrochloric acid because it's a strong acid, which means we basically just have ions floating around. And in this case, the ions that we'd have floating around, we would have some H plus, which is okay because every solution will have some H plus in it. But we'll basically have just a Cl minus floating around, both from the strong acid and also sodium chloride here. So we have a lot of the base part, if you will, of the buffer, but we have no acid part still there. So, and that's not going to allow the buffer to work really well. So you cannot have a buffer that is made up of a strong acid or a strong base. A buffer, first off, a lot of people have a very misconception about a buffer. A lot of people think that a buffer is a neutral solution. And that is true. A buffer can be a neutral solution, but it could also be an acidic solution. It could also be a basic solution. You can make a buffer, frankly, at any pH you like. As an example of that, today we took the yellow, the pink, and the blue solutions. Those were buffered solutions at a buffer of 4, which is acidic, 7, which is neutral, and blue, which is basic, so with 10. So you could absolutely make a buffer at any pH you want. So it's not necessarily always a neutral solution. What it is, though, it is a solution that will be able to maintain its pH, even if you add some more acid or more base to it. And because it has those two parts, an acid part and a base part, it's able to really handle more acid or more base and maintain its pH. So first misconception, buffer always neutral. It is just whatever pH it starts at, it will be able to really maintain it. Will it maintain it exactly where it started if you add acid or base to it? The answer is no. It will go down a little bit. Maybe if you add some acid, pH will go up a little bit if you add some base. But what you will not see is a giant jump in pH. So for example, if you started with a buffer at a pH of 5 and you add acid to it, it should stay around a pH of 5. Maybe it drops to 4.92, 4.93, 5, something like that. But you would not see the pH go from a pH of 5 all the way down like a pH of 1 if you added it, right? And it's able to resist that change. Same thing if we started with that buffer at a pH of 5, you add some base to it, you will see a gradual change depending on how much you added. It will go up a little bit. Maybe it goes up to 5.08, 5.1, something like that. But you won't see the buffer go from a pH of 5 all the way up to like a pH of 12 if you add base to it, if it is functioning correctly. And the way it's able to do that, again, as I mentioned, is there's really that acid part of the buffer and the base part of the buffer. So let's look at actually the action here of buffers and how we get there. So let's first look at a situation where it is not a buffer. So if we take water, which is a non-buffer situation, and if we take some hydrochloric acid, which is a strong acid, and add it to water. So if we take some hydrochloric acid and we add it to water, because hydrochloric acid is a strong acid, it is going to, again, 100% break apart into H plus and Cl minus. So once again, in that beaker, you basically just have a bunch of H pluses and Cl minuses floating around. 100% of what you got going on is those ions. This is really important because if we think about the pH is equal to minus the log of the H plus. So when I dump my HCl into this water, I just generated a bunch of H plus really quickly. So the concentration of H plus went up. That also means concentration of OH minus went down. And because the concentration of H plus went up a lot here, we would expect the pH to go up a lot. Yeah, we would expect a big, sorry, wrong way. We would expect a decrease in the pH. My arrow going the wrong direction. We would expect a big decrease in the pH here as we added more acid, right? So in this case, maybe our water, by the way, the pH of water, maybe about 5 and change or something. If you, we'll say we have pure water. So we'll say a pH of 7. And maybe it goes from 7 all the way down to like pH 2, right? A really big jump in pH because we have a lot of H plus that has been made really, really quickly. So this obviously would not be a buffer because of this. Now, if we took some sodium hydroxide and also added it to water, sodium hydroxide being a strong base in this case, and when we add it to water, it also will 100% break apart into sodium ions and hydroxide ions. So in our beaker here, we basically just made a bunch of sodium ions, but we also made a bunch of hydroxide ions happening here. So by dumping the sodium hydroxide into water, which is not a buffer, we have just increased the hydroxide concentration. By default, that means the H plus concentration went down. And that means in this case, the pH will go up. So we are producing a lot of free hydroxide. And again, 100% of what you got going on there is those ions. None of it's going to stay together. And we would again expect here a pretty big jump in the pH because we basically just introduced a bunch of hydroxide really quickly to our solution. And that's going to make our pH, for example, if we started at 7, maybe jump up to 10 or 11, a really big jump in pH. So in the case here of a non-buffer situation like water, it cannot handle the addition of that H plus to the solution or the OH minus to the solution, and it's going to create a little havoc in terms of the pH. First off, any questions on the non-buffer situation here? All right, so let's look at a buffer and what would happen if we added these things to a buffer. And we'll just use a different sort of situation since we've been using HF. Why not? We'll use HF and we'll say we made a buffer out of these two things here and some sodium fluoride. This once again is our weak acid and the conjugate base. And again, even though it's sodium fluoride, the sodium is just a spectator ion. It's really not doing anything. The sort of buffer part of it, again, here is really the F minus part. So we have HF and F minus, which again is that relationship of 1 H plus difference. And we really have, again, an acid part and a base part in the solution. So in this solution, it is going to, as I drew before, able to set up this equilibrium. And again, we have that acid part in the solution and the base part in the solution. So now if I take that same acid that I put in there before, and I decided to add some HCl to this solution, I'm going to get a reaction between HCl, which is a strong acid. When I dump HCl in here, and it goes for a swim, it is going to react with what thing? Will it react with the acid part of the buffer or the base part of the buffer? These reactions are called acid, what type reactions? Acid-base reactions. Yeah, they're not called acid-acid or base-base. Kind of just sounds funny, right? So when you dump this strong acid into the solution, it is going to go and really react with the base part of this solution, which is our buffer. And we will get this reaction. And again, if you want to leave the sodium fluoride, you can. R is really the F minus part. This is going to do a double displacement reaction, right? Positive, negative, positive, negative. So we're going to get a switcheroo that's going to happen here. And the result of this is we will end up with HF being formed. And we'll resolve a little sodium chloride action. So by adding this to our buffer instead of water, we actually get this reaction that occurs. And this is really important. Let's take a look at what we made. So in this particular case, we made more HF. HF was part of the buffer to begin with, right? So we actually just increased this guy in that solution, right? We made more of this guy. Now, the other thing that we made was a salt here and the salt is sodium chloride. So with your advanced salt skills, right? You're going to tell me sodium chloride is what type of salt? It is a neutral salt. I think I heard somebody say that, so that's good. That is a neutral salt, right? That is a sodium ion, which is group 1, which is neutral, and Cl minus comes from HCl, which is a strong acid, which means it will be relatively weak and neutral as well. So we made a neutral salt, and we made part of the buffer that was there originally, and that always happens. You always actually make part of the buffer when you use part of it. So in a buffer sort of reaction, you use up, in this case, some of the base part of the buffer, but you actually regenerate a little bit of the acid part in this case. It is actually what we do not see here that is really important. So what do we not see here that we did see when we added the HCl to water? What is not in that equation that is in the equation for it when the acid when it was added to water that would affect the pH? Yeah, and what ions particularly is important here? What affects pH? Yeah, so when we added the HCl to water, we made a bunch of H+, right? Which has a really big effect on the pH. When we added that same acid to here, there is no free H+ formed. So we don't actually see that H+ being formed. And what that means is the amount of H+ that was there originally will remain relatively constant. So because no new H+ was formed, the concentration of H+ stays relatively constant. And if the H+ concentration stays relatively constant, that means pH should also stay relatively constant as well, because the H+ concentration is not going crazy at this point. It pretty much is hanging out around where it started at, right? It will change a little bit, so you will see that pH come down a little bit, but you won't create as much H+ as you did with that non-buffer situation that you'll see a really big jump in pH. We obviously are making some more HF that will kind of break apart a little bit, right? And make a little bit more H+, and that's why we see a slight decrease in the pH and not a big jump. So when we add that strong acid to this buffer, because there's a base part to this buffer, which in this case is our HF, right? It is able to prevent the formation of free H+ and thus keep the pH relatively about where it's at. Any questions on that there? So let's talk about what happens when we add the sodium hydroxide here to the same buffer. So if we added our sodium hydroxide to our same buffer, so same idea here, we have our buffer that is set up with our HF, our H+ and F-. And in this case, we're going to add some sodium hydroxide to it. When we add the sodium hydroxide to this buffer, it should react with what thing? Should react with the acid part of the buffer, which is HF. So we're going to get a reaction, in this case, between sodium hydroxide and the acid part of the buffer, which in this case is HF. This is going to do a normal acid-base reaction, which you make water and a salt, also a double displacement reaction. Positive guys switch partners to make water and our salt in this case, which is sodium fluoride. Right? So in this particular case, we see that we made water, which obviously would not affect the pH. Just like we saw above, in this case, we actually made some sodium fluoride, which is the other part of the buffer. So we actually increased the amount of sodium fluoride in this example. Which again, it always happens in a buffer situation. Once again, you kind of use one part of it and make the other part. So as one goes down, the other part of the buffer kind of goes up. So once again, that sodium fluoride, which was there to start with, should not mess up the pH. Water obviously should not mess up the pH. And once again, it is what we do not see that we did see here. What did we see here that was important? When we added the sodium hydroxide to water, we saw a bunch of OH minus being formed. And in the reaction with the buffer, we get no free OH minus being formed. And that's really important because as we've been talking about, H plus and OH minus, their concentrations are pretty much tied to one another. So if the concentration of OH minus stays relatively constant, that means that the concentration of H plus will also stay relatively constant. Remember, as one goes up, the other goes down and vice versa. So if one stays constant, the other will stay constant. And that will keep our pH, again, relatively constant here. Will you see it move a little bit? You will. You'll see it, again, come up a little bit. But because we're not generating a ton of OH minus all at once, we will not see that really big jump in pH, but maybe it goes up a little bit as you're adding the base. Yes. Where it says after which word now? I'm sorry. pH stays relatively constant. Is that what you're saying? Is that what you're talking about? Or above that, the OH concentration is relatively constant. The H plus concentration is also relatively constant as well. And both of those being relatively constant. And again, I say relatively constant because there will be a little bit of movement in those concentrations, but not big changes in those concentrations that we see a really big jump in the pH up or down. And that's how it's able to do it. Question on either of that there. So the way a buffer is able to function is because it has an acid part and because it has a base part, it is able to prevent when you take some acid or base and put it into a buffer, it's able to prevent the formation of free H plus or free OH minus. And by preventing more of those H plus or OH minus from being formed, it's able to keep those concentrations constant and also keeps our pH from going crazy and relatively constant as well. So sometimes you could think of a buffer sort of like this. You know, you have, if this is sort of our buffer, and it has, again, an acid part and a base part. And when we add additional acid to it, it is going to react with the base part, but it will make some more of the acid part. So dramatically drawn here, we will make more of the acid part, but we'll use up some of the base part here. Not drawn to scale in this case, if this is still our buffer. And if we add some base, we will use up the acid part of the buffer, but we will make more of the base part of the buffer. So you can think about it as a buffer is sort of working, you're sort of using part of it, but you are sort of regenerating the other part of the buffer. So you're kind of like going up and down depending on what you're adding. Now, there is something known as buffer capacity. What happens if I didn't read instructions, which I'm sure nobody would ever do, and I grab the wrong thing off the shelf? Like I grab the, say, 18 molar hydrochloric acid instead of like the 0.1 molar. Could happen. It seems very similar, I suppose, right? Besides the fact that you'd be choking and the tester would get really hard, and you dump it into your buffer, right? So let's just say I added like way too much acid, too strong of an acid, too much volume of an acid. What would happen in that situation if I added like way too much acid? As I continue to add acid, I am basically going to continue to do what to my buffer? I'm going to continue to chew up, right? The base part of the buffer, right? This part will keep growing. This part will keep getting chewed up, until some point you chew up all of your buffers, kind of like blowing through your buffer, right? And now if that doesn't stop you at that point, and you're like, I still got like 30 gallons of acid, why not? We'll just keep dumping it in. Once you blow through your buffer and you keep adding that acid, what's going to happen? It is, because now all you're doing is dumping in a bunch of H plus, right? At that point, that there's nothing in that solution anymore to stop it from forming. And as you correctly said, you would see a big jump, right, in the pH coming down. Same thing would happen if you added too much base or continue to add base, added too strong of a base. You could blow through your acid part of your buffer, right? And at that point, you would just continuously add OH minus to it, and you would see a really big jump in the pH at that point. It would go up. It is basically what happens, and we'll see it, and we'll talk about when we do titrations. But if you've ever done a titration before and you add just one drop, right, and your thing went from colorless to like super pink, you blew right through your buffer, basically, is what happened there. And you had a really big jump in pH. And that's why it went so dark pink on you when you did your titration. We'll talk more about that when we get to a titration. But that's kind of a similar situation. So there is a limit to buffers. When you make a buffer, and we're going into the buffer experiment, I think coming up next on Thursday, we're starting it. When you make buffers, you do want to make a buffer that is sort of the correct molarity, if you will, to react with the acid or base that you may be adding. And again, it's about really the moles of your buffer and stuff like that.